Remember this? In the previous video, part 3, we explored statistical significance and stated that if we found the p-value to be less than 0.05, i.e. 5%, then we could say that our results were unlikely to be due to chance, i.e. we could reject the null hypothesis of no difference, and so accept the alternate hypothesis and conclude that the difference seen was real, i.e. was not due to chance. We decide whether to accept or reject the null hypothesis by using inferential tests. These come in many varieties. It is how the researchers choose their test that is important. Now, many textbooks offer flowcharts or decision trees to help the researcher select the most appropriate statistical inferential test for their research. The one I'm using here is taken from Green and Oliveira with the modification from Pallant. I would also recommend looking at the flowchart offered by Andy Field's Discovering Statistics Using SPSS book. This is also the book I would recommend to take you to the next level, i.e. if you are carrying out statistics for yourself. I will give a slide at the end with all these references on. Now, this decision tree is a series of questions which are followed by branches that are further followed depending upon the answers. We start at the top and center, and we are first confronted by our first question, namely, what sort of comparison can your data offer? So we initially choose from categories, differences, or correlations. For example, if our data has been collected into 2 or more groups, but is only at the nominal level, also known as categorical in American textbooks, then we only have one test available, the chi-squared test. This test is also known as the Pearson chi-squared test. Now we have to be clear what we mean here. A nominal, i.e. categorical level variable, is a grouping variable, and this applies to many research designs. However, whilst a great deal of research measures higher level data, such as interval or ratio, e.g. blood pressure or your COVID age, we use the chi-square test only when we have counts in these groupings, such as men versus women, or how many people voted for each political party at the last election. In the first video in this series, I explored with you this hierarchy of data types. Let me quickly remind you here what this is. There are 4 levels: nominal, ordinal, interval, and ratio. And the sense is that the higher up that list you go, the more sophisticated, as it were, your variables are. Nominal level data, which I've also called categorical data, is where you have categories in which you can only really count occupants, e.g. number of men versus women. Ordinal level data is where the data has a natural ranking, and many surveys utilize this in what is known as Likert scale type questions, where you tick a box for good, better, best, that kind of thing. Interval level data and ratio level data are both measures where we recognize them as such. However, interval level data is data with an arbitrary zero. It can go negative, e.g. degrees centigrade, whilst ratio level data cannot go zero. It is data with an absolute zero. But for further information, I refer you back to the first video in this series. Now let me give you an example of when we might use the chi-squared test. Suppose I am interested in exploring whether the differences between the number of men and women employed in different sectors of nursing might be within expected statistical fluctuations, or if something else is going on. This data is taken from Reed and Bohr, and you can see that whilst in total there are more men than women, there's 120 women versus 80 men, i.e. in the ratio 3:2, this is certainly not reflected across each sector. The standout category seems to be admin, which by the way includes management, i.e. the higher paid jobs, and I'm suspicious that more men than women are being employed beyond what I might reasonably be able to explain as just a random fluctuation. Of course, a chi-square test cannot explain any discrepancies seen, but it can certainly flag them up as sufficient evidence to warrant further investigation. If, on the other hand, we have 2 variables measured for each participant, and these are higher than nominal level, say shoe size versus height, which would be ordinal and ratio respectively, then we may wish to simply compare measures and a correlation test would be used. These tests are typically used for observations rather than measuring the outcome of an intervention. You will notice there are two types of correlation test, and the choice you will make depends on whether the data measured is parametric or non-parametric. I will say more about that later. An example of a correlation test might be if I want to explore the possible relationship between current salary and number of years experienced amongst employees at a large company. Now, as we can see from the flowchart, most tests are exploring differences seen across two or more groups. Such scenarios include classic research interventions such as randomized control trials, RCTs, but there are many other designs which could come under this definition. So this area of the chart is considered if I have two or more groups. Again, the data must be higher than nominal, so this would rule out a chi-square test, and furthermore, it is now typically an intervention. Of course, such tests can be used in observational studies, but with more extensive data than a simple correlation, but which are not therefore strictly speaking experiments. But an analysis of differences across such groups can still throw light on differences seen across these groups or over time within groups. In other words, in such cases, therefore, the choice of which test to choose requires more thinking, or rather more decisions. An example of this might be, suppose I teach two classes. In one class, I teach the national curriculum as prescribed, but in the other, I use a novel approach involving a short group meditation at the start of each lesson. I am interested to know if there is a genuine difference in their end-of-year evaluations that could be attributed to this intervention. So in summary, if we have two or more groups and the data is higher than nominal, i.e. is ordinal, interval or ratio, and this is now typically an intervention, then we must choose a differences test. A crucial point, often missed in reading and carrying out research, is that groups must be allocated using some sort of randomization method. Now, what do I mean by random? Well, not random in the sense of completely arbitrary and chaotic, but more when a procedure has been utilized involving probabilities of selecting to ensure the groups have similar characteristics at baseline and fairly represent the population from which they are drawn. If such probability sampling has not occurred and the groupings are selected using some sort of convenience sampling, then there is a strong possibility of bias, and any statistical significance subsequently measured, remember p less than 0.05, in any of these tests might be spurious and therefore invalid for drawing any conclusions. Let's explore further the choices involved in such differences tests, as clearly this is the more involved of the three choices. We first need to decide on the number of variables we are measuring, and note we do not count the grouping variables here, only those variables we have measured such as height, weight, blood pressure, that kind of thing. Let's suppose we are only measuring, or rather analysing, one outcome variable to keep things nice and simple-ish. We might be careful here, as what this question means is how many outcome variables are we concerned with, not how many grouping variables, i.e. groups, there are. That question of course will come next. So this chart tells us that there is only one variable of interest, which is the number of deaths. We are then asked how many experimental conditions are there. This simply means how many groups are there in the design. The simplest design is two, such as a control group and an intervention group. Notice here that even if you are looking at a before and after design, we would regard group 1 as everyone at the beginning, before the intervention, and group 2 as those same people at the end, after the intervention. So even with a before and after design, we still analyse it as two groups, where incidentally each person acts as their own control. So RCTs could also have this feature and still be regarded as bona fide RCTs. Next, we are asked if this is a between groups or within group study. A within group study is typically the before and after design I have just been talking about. However, we might also sometimes consider comparing husbands and wives or siblings as within group studies. For example, I once read a piece of research looking at depression levels as measured by some sort of quantitative scale. for married couples who had lost a child to cancer. In each case, for each wife, there was a husband linked via their child who had died. A between group study, on the other hand, is where the groups are comprised of different individuals who are not related in any way. They are also known as independent groups. The classic example is the randomized control trial for an intervention, such as a new antiviral drug, where we have one group who receive the new drug, the intervention group, and another group who receive a placebo, i.e. a neutral drug, and these are called the control group. Notice a between groups design should be blinded, where each participant does not know which arm of the research they are in. If this has not happened, then we are back to the possibilities of unknown biases creeping in and our results, the p-values, etc., possibly being invalid. Now, the final question before we can decide which test is the appropriate one to use is whether the data is parametric or non-parametric. Now, this is a bit technical, but we would like to use a parametric test as we are then more likely to get statistical significance, p less than 0.05, and therefore more likely to reject the null hypothesis. This is because parametric data is generally deemed to be of a higher quality, so to speak. To be considered parametric, our data should pass 4 quality control criteria. The first criterion is being normally distributed. In other words, the variables measured for each group should be normally distributed. See the last 2 videos in this series for more about that. It simply means that our data has the symmetric shape known as the normal distribution, and crucially, if our data is not normal, if it is skewed, it would then be considered non-parametric. The second criterion is that our data must be interval or ratio, and we explored this in the first video where we looked at the hierarchy of data types, which I've already reminded you of. If the data is ordinal or nominal, then it cannot be regarded as parametric, i.e. it would be instantly relegated to be non-parametric. The third criterion is that our data must be continuous. In the first video, we looked at the difference between discrete and continuous data. Continuous data, in essence, are measures that could, in principle, be measured to ever greater degrees of accuracy, e.g. to more decimal places, whereas discrete data, which are typically whole numbers, do not have that feature. The fourth and final criteria is something called similar variances. Now, we briefly mentioned standard deviation in the first video, and the variance is simply the square of the standard deviation and is a more commonly used statistic as a measure of spread by statisticians. Now, this word similar seems a bit vague, doesn't it? If you think of 2 groups with standard deviations 4 and 5 respectively, at first glance it seems they have similar spread. But remember, the variance is the square of the standard deviation, so we're actually comparing variances of 16 and 25 respectively, not so similar after all. However, those textbooks that do give more guidance say that as long as the higher variance is no more than 3 times that of the smaller, we can safely call the variances similar. So that's okay then. A final word on these parametric versus non-parametric shenanigans. A lot of research, and I do mean a lot, seem to be very relaxed about strictly sticking to these criteria. We have just seen this sort of with similar variances. Another common one is having discrete data instead of continuous data and yet still treating it as parametric. I used to really worry about this and insist that they were all wrong. Well, I now realize that statistics is very often an inexact science. A good example is the marking scheme for exams and written assignments, which are often set up to produce a percentage, a score up to 100%, but the marking scheme can only produce whole number values, integers remember, which of course are discrete. Well, the thinking seems to be that as there are so many possible discrete scores, then from a distance they could be regarded as continuous, sort of. Also, they can certainly be regarded as ratio in the sense that a score of 80 is definitely twice as good as a score of 40, so we can give this kind of data a pass for this criteria. Now let's suppose I know the correct test that should be used. Now what? Well, as readers or consumers of research, we are only concerned with judging whether we think the researchers themselves have used an appropriate test for their study design and type of data. The key outcome we will look at is of course the p-value, or if we are feeling brave, the confidence intervals of differences. In other words, we simply want to know if their analysis produced statistically significant results. We leave it to SPSS and other computer programs to actually carry out the tests, and we trust that they have done so correctly. Now, for this final bit of the video, I want to run you through a pretend bit of research just to see other aspects that can arise. And I want to look at something called modelling variance. The idea of variance across our dataset is actually the fundamental concept that statisticians use to explore relationships beyond the tests shown in the early flowchart. In fact, many of those tests do look in detail at the variance, i.e. the variation of scores from person to person and from group to group. This deeper analysis, extending beyond the flowchart, is known as modelling, and it is a process where we try to understand our data and the phenomena behind it by finding an equation that explains the variance measured. So let's look at a non-contentious example to illustrate this. So let's pretend to build our own multivariate equation. It will end up looking something like this, where each of the x's represents a different variable and each of the a's represents a number which is a weighting or risk factor. For example, x1 might be gender, x2 might be age, x3 might be the sector of work, etc. The first term, a0, is a constant. It is not attached to any variable. We could think of it here as perhaps the lowest possible pay level. And the final term, epsilon, is a random term, hopefully a small value that acknowledges that there will always be some uncertainties and fluctuations in the pay that are simply impossible to model. Now, before we can even begin to build an equation, we need to identify all the factors that could possibly influence a person's pay, and not just the ones I have already suggested. The most obvious of these for our interests, of course, is gender, but we must explore as many avenues as possible in order to see which factors, gender included, are really driving someone's pay. If we are too selective here, then we are in danger of proving by assumption, and we are, of course, back to biases again. An example of such a list of some of the possible factors is given in this mind map, and it is in no way meant to be seen as complete or exhaustive. Clearly, in a real piece of research, there will be a lot of thinking going on here, including surveys, interviews, and poring over as much data as we can find in order to identify relevant variables that we can then go out and measure. Now, supposing we have identified a finite set of key variables for this study. As an example, these may include gender, age, number of children or dependents, highest level of education attained, or even just the number of years spent in full-time education, number of years in the job they currently occupy, the sector of work they are in. After all, working as a shelf filler at Lidl is possibly less lucrative than working in the financial sector, marital status, socio-economic background, etc., etc. Of course, in addition, for many of these factors, we might also have to think very carefully about defining what is meant by gender, marital status, level of education, etc. Okay, having identified all the variables we wish to explore, we will next go out and access a large and wide sample of randomly produced participants and their associated data in order to make our results applicable to the population at large. And once the data is in, we will then use a computer program such as SPSS to fit something called a regression model, which is the fancy term for this equation we are seeking, and we end up with something like this. Of course, each of the A's would now be an actual number to indicate the weighting associated with that variable. And these numbers, these A's, are called coefficients, and they are not limited to any particular range, but simply reflect the importance that has been objectively calculated for each variable or factor. Those identified as the most important are sometimes called signals, in that the researcher can claim the most important signals indicating pay are, for example, age, gender, and ethnic background, in that order. It is this endpoint of quantitative research that sets it aside from qualitative research. So long as we've been careful and fair and unbiased in collecting our data and deciding the range of variables to collect, then we do arrive at a much more objective conclusion than we could possibly have done via a qualitative approach. Now, an example of an actual regression equation is given here in all its glory. Notice now, instead of age, we have actual numbers. The fact that some variables are nominal, such as gender and education, are possible is because the researcher has done something called coding, where the researcher has set, say, male equals 1, female is equal 2, etc. Also, all of the initial variables explored may not survive into the final model because the computer will determine which are the most important variables to explain the variance. A more complete exploration of the variance of all these variables into such a model would also have to include what are called interaction terms. For example, it might be that being female or a person of colour may not individually mean your pay is particularly low, but if you happen to be both, then together this has an adverse effect on your subsequent pay. We can see such a interaction term here in green, where ethnicity star gender, meaning the variable ethnicity times the variable gender, is the interaction term. This interaction term will also have its own coefficient, its own A value. Of course, our final and ultimate model may include more than one interaction term between different pairs of variables, and it is of course possible that we have interaction terms between more than two variables. However, the important job for the statistician is to tease out and model only those most important variables and, if necessary, important interactions, because ideally the model should contain as small a number of variables and interactions as is necessary to explain the bulk of the variation seen in this case pay. If we have too many variables in our model, it becomes too ungainly and possibly unusable. Statisticians and researchers must, after all, produce results that are understandable and useful to the wider community. Finally, I have included a link to an interesting Channel 4 news interview between Kathy Newman and Jordan Peterson that uses some of the terminology I have used here, and this sheds further light onto this issue. The link is given in the description below. It is a good example of calm, considered conversation where there is absolutely no suggestion of cheap point scoring on either side. Okay, I never said statistics wasn't ever feisty. Once again, thanks for listening, and I leave you with some references.